Good day, I'm Victor Salanga and my design project is a 10m Optical Wireless Temperature Transmitter. Temperature sensing is a vital process in our daily lives. In order to monitor one's well-being, temperature sensing is being utilized to be able to detect if a person is sick or not. This is especially useful in today's time where a global pandemic crisis is happening. Furthermore, temperature sensing is not only limited for human uses. It can also be employed through different mechanical and electrical purposes. For equipment or places that are dangerous or inaccessible to people, temperature transmitters may prove reliable and essential in order to measure and monitor its condition. The information it obtains will then be sent to a receiver station to process and interpret it, conveying reliable and useful information. The goal of this design project is to provide a setup for a 10m optical wireless temperature transmitter. It also aims to provide a detailed analysis about its components and its respective functionality. First, let us choose a temperature sensor. There are different types of temperature sensors available in the market. It could be a resistor temperature detector, a thermocouple, a semiconductor sensor, or a thermistor. For this project, we will use a semiconductor sensor, which is the TMP36 low voltage temperature sensor. The TMP36 sensor can detect temperature from -40 degrees Celsius up to 125 degrees Celsius, converting it to an output voltage. As you can see in the figure, the TMP36 is powered by a battery, then it detects the temperature. The temperature is now converted into voltage, which is read by a voltmeter. But how did the temperature get converted to voltage? The answer lies within the sensor's internal circuit. As you can see in the figure, the core of the TMP36 sensor is a bandgap core that comprises transistors Q1 and Q2, biased by Q3 to approximately 8 microamperes. The bandgap core operates both Q1 and Q2 at the same collector current level. However, because the emitter area of Q1 is 10 times that of Q2, the VBE of Q1 and the VBE of Q2 are not equal. This is shown in the displayed equation. Resistors R1 and R2 are used to scale the result in the displayed equation to produce the output voltage transfer characteristic of the sensor. And, simultaneously, R2 and R2 are used to scale the VBE of Q1 as an offset term in Vout. The output voltage of the temperature sensor is available at the emitter of Q4, which buffers the bandgap core and provides load current drive. The current gain of Q4 working with the available base current drive from the previous stage sets the short circuit current limit of the device to 250 microamperes. Now that I've explained how the TMP36 sensor works, let's set it up for testing. The schematic diagram for it with all the necessary components is shown in the figure. I assembled the circuit in Tinkercad and the output is shown in the figure. As you can see, the temperature had been converted by the TMP36 to produce the 48.3 mV displayed by the voltmeter. By changing the temperature detected by the sensor, the voltage read also changes accordingly. When we set the temperature to -40 degrees Celsius, the voltage read is 60.44 mV. When we set the temperature to 125 degrees Celsius, the voltage read is 113 mV. This will be the sensor's configured output voltage limits. Now that we saw our sensor works, let us build the 10m optical wireless temperature transmitter. Shown here is the block diagram. First, the temperature is measured. Then, the transmitter emits a light. After that, the receiver detects the light. Next, the light is converted to temperature in degrees Celsius. And finally, the temperature in degrees Celsius is displayed as voltage. For the transmitter block, the output voltage from the TMP36 temperature sensor will be amplified in order to power up the super bright LED that will be attached to it. In order to do this, two operational amplifiers will be connected. The first one is a differential amplifier that subtracts 6.4 mV from the sensor's output voltage. The output from it will enter the second one, which is a non-inverting amplifier that multiplies it to a gain equivalent to the slope of the circuit input voltage and the TMP36 voltage output, which is 47.353. The output from it will enter the super bright LED for it to have a variable intensity depending on the output voltage of the sensor. This dictates when will the super bright LED be on or off and how much light it will transmit. The schematic diagram for the transmitter block is shown in the figure. To process the light emitted by the transmitter, we will need a receiver. For the receiver block, I designed it to have a photodiode and two operational amplifiers. The photodiode that will be used is the SFH2505. It will detect the light emitted by the transmitter and convert it to a voltage. This voltage will enter the first operational amplifier of the receiver. The first one is an inverting amplifier that multiplies the output voltage from the photodiode by the gain equivalent to 10 times the slope of the transmitter detected temperature and photodiode voltage output, which is approximately 4. The output from it will enter the second one, which is a summing amplifier that increases it by 10 times the negative equivalent of the coldest temperature the sensor can detect, which is -40 plus 200, that is equal to 1600. The output from it is the actual detected temperature by the transmitter with a certain multiplier and offset, which is displayed in volts that will be read by a voltmeter. Now that the transmitter and receiver blocks are done, the 10m Optical Wireless Temperature Transmitter is complete. Shown here is the complete schematic diagram of the transmitter and the receiver. To be able to relay the signal from the transmitter to the receiver for as long as 10 meters, I designed an optical covering for the super bright LED and the photodiode to be able to detect the light emitted without adulteration. This is shown in the figure. As you can see, it covers both the LED and photodiode completely. You can think of it as a pseudo fiber optic cable that can deliver the light for a long distance. I assembled the circuit in Tinkercad and the output is shown in the figure. Here is the simulation of the 10m Optical Wireless Temperature Transmitter in Tinkercad. The separation distance between the transmitter and the receiver is not shown here since the demonstration is for the performance of the sensor and its readings. Let's just say there is an optical covering that we can put here. As you can see, when I change the temperature detected by the TMP36 temperature sensor, the voltage read by the first voltmeter changes accordingly. This is amplified by the two operational amplifiers to light up the super bright LED accordingly. As you can see, it turns on and off with varying intensity. The light emitted by the super bright LED will be detected by the photodiode. As you can see, when I change the amount of the light detected by it, the voltage read by the second voltmeter changes accordingly. The way it is configured is done by the two operational amplifiers I have discussed earlier. Okay, now let's set up how the system will work. First, let us set the detected temperature to the sensor's lowest threshold. Since this is the lowest temperature, the super bright LED will technically be off. Because of that, the photodiode will have no light to detect, so its configuration is set to darkest. As you can see, the voltage from the second voltmeter is 1.60 volts. To be able to determine the temperature, this voltage must be multiplied by 100, then subtracted by 200. As you can see from the equation, the answer is -40. Therefore, the actual temperature detected by the 10m Optical Wireless Temperature Transmitter is -40 degrees Celsius. Now let us set the detected temperature to the sensor's highest threshold. Since this is the highest temperature, the super bright LED will technically be on. Because of that, the photodiode will have detected all the light, so its configuration is set to brightest. As you can see, the voltage from the second voltmeter is 3.25 volts. Again, To be able to determine the temperature, this voltage must be multiplied by 100 and subtracted by 200. As you can see from the equation, the answer is 125. Therefore, the actual temperature detected by the 10m Optical Wireless Temperature Transmitter is 125 degrees Celsius. And that is my designed 10m Optical Wireless Temperature Transmitter. The 10m Optical Wireless Temperature Transmitter had been analyzed and dissected through its components and functionality. The sensor used is a TMP36 low voltage temperature sensor. Its circuitry makeup and incorporated components had been tackled and explained. The transmitter used a super bright LED to be able to deliver its optical applications. The receiver block had also been given focus. It consists of a photodiode in order to detect and process the intensity of the light emitted by the transmitter. The sections incorporated to the transmitter block, such as the differential and non-inverting amplifiers, as well as the receiver block, such as the inverting and summing amplifiers, have been elaborated to give a perspective regarding the system's operation. Through the setup of this design project, it can be inferred that commercially available 10m optical wireless temperature transmitters in the market operate similarly, if not purely identical, to the electronic circuit discussed here. All things considered, the goals of this design project had been met for the setup of a 10m optical wireless temperature transmitter. That concludes my presentation. Thank you very much for listening.